Sir, you can start. Meanwhile, if they connect to the internet, we will ask you some questions.
Okay, sir. I think someone has switched on their video and they are showing.
Sir, your voice is very low.
Sir, someone has switched on the video and they are trying to show something, but the image is tilted. I'm not able to see. Yeah, please share the screen. It will be easy for me.
Yes, sir. We will share the screen.
Okay, okay. You want me to wait, sir, or shall we proceed
No,
with
sir.
the new topic?
You proceed. If it is connected, we will ask.
Okay, okay. No problem. Okay, welcome back, participants, for the afternoon session of day two. Uh, till now, we have seen we have understood the entire FPGA design flow, right from the design specifications and HDL description, synthesis, implementation, bitstream generation, and implementation on FPGA by using a simple logic gate example. So this is a combinational circuit, but now we have not addressed any sequential logic based design. So I would, in this session, I would like to cover a small example on sequential logic circuit design as well. And then because if you take into consideration the real-time systems, you will be having a mix of combinational and the sequential. So you should be aware of how to deal with a combinational logic, also how you need to deal with a sequential logic. So for the purpose of today's FTP, I have taken a simple counter-based design. So we will design a simple counter and then we simulate it. After that, we try to implement it on FPGA and see the output. So it will is gonna be a simple up counter. So what is my advice to all the participants is, due to the limitation of time, we couldn't do many examples on combinational as well as in the sequential. For combinational, I have taken only simple example. I think Dr. Mahesh sir has given, as instructed you to design various circuits like adders, multiplexers, decoders, encoders, etc. So after the FTP program, I suggest you people to spend some quality amount of time in designing the circuits. It is not necessary to implement each and everything on the FPGA. Only thing is you should be very much familiar with the flow. I think the flow is very much pretty clear to everyone. So only thing is you need to get familiarized with the Verilog language, and if any specifications is given, how you will be coding that circuit, how you will be coding that description, HDL description using any of the HDL language. So that is main important. So spend more time on writing the Verilog codes, customized codes on yourself, and try to simulate it and check the functionality. After that, do synthesis and implementation. Check whether they are getting error free or else any errors are coming or not, and try to rectify. So if you practice in this manner, then only you can enhance your skills. uh, it's not mandatory to generate bitstream and do implementation. Maybe I understand that everyone will not be having access to the FPGA board, so at least be familiar with the design flow as well as the language, the way of writing Verilog descriptions, and the way of performing synthesis and implementation. So without wasting much time, we will start with the second lab experiment, that is a sequential circuit design, wherein we will be looking at design of a simple counter. So allow me to share my screen. Invoking my viewer. I hope that my screen is visible, right?
Yes, sir.
Yeah, yeah. Okay, thank you. Yes. Sorry, I got one important call. Okay. I am at the home page of Verilog. So I'm just creating a new project. Those who have completed all the experiments, you kindly switch to this new experiment and try to follow along with me. So I'm creating a new project in the same day one folder itself, and naming the project as lab 2. Okay, next, it's an RTL project. I'm just speeding it up. Why? Because I think these details are very much familiar as of now to everyone. So I'm selecting basis tree board XC7835T CPG 236-1. A project environment is being created. Yes, so we will add a new design source. Just a minute. Yeah, make sure your target language is Verilog. So now I'm giving a name to this folder as my counter. So what type of a count we will design at least a 6-bit counter. So give any generic name. So under the design sources, you can see my counter 6-bit. Verilog file has been created. So just quick notes. Let me open my MS. So we are interested to design a counter. So assume that this is a 6-bit counter. This is a black box, and so since counter is a sequential logic, it is going to have a clock signal input, and it should also needs to have a reset signal, because since it is a sequential logic, a memory kind of we'll be storing a data right in the registers. So before we start any operation, we need to clear the register or reset the register to the initial states. So to reset all the internal registers, we need to give a reset signal, and we have a enable signal. So when enable is high, then the counter starts counting in the upward direction. So actually we are designing a 6-bit up counter. Okay, and then these are the inputs, and we have here the count value. So at each and every clock cycle, the counter will increment its value by 1, and the count value will come out on the count output. So this is a simple configuration we are taking. Even if you want, what you can do is you can add maybe additional outputs like a flag. You can add extra inputs like whenever the counter reaches a maximum value, you can use a flag output to indicate like maximum count has reached, just like or else done take some kind of a signal. But we are only concentrating on 3 inputs and 1 output for to keep it very simple. Now we will see how we will be designing the counter. So the basic is the conditions. Initial condition is, what are the initial conditions of our counter? The count value should be 0. Since it is a 6-bit counter, so the maximum value is 2 power 6 minus 1. So this is the range. 2 power 6 is 64, right? 64 minus 1, so 63. So the counter will keep on counting the states varying from 0 to 63. So this is a decimal counter. Other name is also decimal counter. Okay. And initially, since we are saying it is an up counter, the count value by default should be 0, and it should also start from the 0th count. And counter should start counting. It should start counting only when enable is high. This is our condition. High in the sense logic high or else logic 1. And it should not count when enable is low. When enable is low, it should not count, and it should retain the last counted value. Understood? Again, when the enable is high, again it should resume the count and it should proceed from the last stored value. So these are the conditions. Again, when you press any reset, the count should become 0. So these are the conditions. So whatever I have described, this is the user specifications. So now we got the specifications. We need to design the counter. So how do we proceed? So we have created our module, and my module name is my counter 6-bit, and at the end we have an end module. And coming to the port list, first we define the input ports. So input, we have a clock input. Next input, we have a reset. Next we have another input called enable. And output, since at the output we need to get the count value, and the count value, minimum value is 0, maximum value is 63. Since it is a 6-bit, so 0 to 63, total 64 states. To represent 63, we need 6 bits. So 6 bits means it is a bus. So how we will define 5 down to 0, that is 6 bits, and count value. Okay, am I clear? So we have defined the port list. Now our black box is ready. Now what we have to do, inside the black box, how the circuit needs to function. For that we need to describe it using RTL. So here one thing what you need to remember is, so we have a black box, we have a clock, we have a reset, and we have enable, and we have count. Now what is there in this black box? So that is important. So since I'm telling it as a counter, basically it should be having a counter register. A 6-bit count register. Register means it's nothing but a flip-flop. Flip-flop means it is a sequential circuit. Maybe you'll be having a clock. Something like this. A common clock. And D input. Okay. So here what is the intent? My intention is, okay, for example, we consider only you consider this is the register, So down the line you have 6 flip-flops to hold 6 different values. You have a data D, you have an enable input. Okay, when enable is high, it should take the data, and this is the clock input. So this how the count value is always stored in the register, and count has a Q output. This is driving the count output. Correct? The register value is driving the count output line. So output is a wire. Internally we are realizing a register. In the register we are storing the count value. So how this count value is getting updated? Just a minute. Yeah, sorry for the interruption. So the idea is we have a register D and data is coming, and this is a clock. We have a Q output. This is a series of flip-flops. So this is treated as a register, and we have a count output line. So we are driving the count output line via the register. So the count value we are storing in the register, and that value is driving the count. So how this count value is updated means, so basically at each and every clock edge, we need to increment the counter, right? So the count value needs to go to a adder circuit, and then it needs to be incremented, and it needs to drive the D output. So actually what's going on here means, so we have a register over here. This is a sequential logic, and we have here some combinational logic. So this is D, this is Q. The sequential logic is will work with respect to a clock. So this output, this is output line, this is count. So what we are doing is this output we are just feedbacking to the combinational logic, and the combinational logic will calculate and it gives the value to D. So what is inside this combinational logic means, so basically we are having an adder. So it's taking the feedback output from the register, and then it is incrementing by 1, and the incremented value is fed to the T. So this combinational logic will work independent of the clock. So whenever if our flip-flop or a register is a positive edge triggered, during this instant, whenever this positive edge is coming, then what it will do, it will take the value, it will read the value on this input line D, and that value is stored in the register. And this value at the same time is fed back to the combinational logic. And here we will be developing some logic with respect to enable input. If enable is high, then only the value will be incremented and it will pass to the D. Otherwise, if enable is not high, then we don't increment the value, we pass the value same as it is. So for that configuration, what we do is, you can assume like in the combinational logic you might be having a multiplexer where the select line is the enable, and when enable is 0, it should give the Q value. So here the flip-flop D and this is Q. Q value will go. When enable is 1, the same Q value incremented by the adder, incremented by 1 will go, and this register will sample that value at the arrival of the next clock edge. So this is a phenomena that is going to take place. So the main thing that you need to keep in mind is, we have a sequential logic that is works with respect to a clock, and this sequential logic gets updated on every clock edge, either a positive clock edge or a negative clock edge. And how it is getting updated, the corresponding combinational logic will compute the next state value, and it will pass it to the register, and it will be kept on this line. When the next clock comes, at that time it will sample that value will goes into the register. So this is the main key idea. So here, with though we have a combinational though we are dealing with a sequential logic, we also needs to make use of the combinational logic in order to update our sequential logic, that is the register. So when coming back to the our main counter design, so module my counter 6-bit, so we have clock, reset, enable and count. So how do we proceed? So first we will create a register. We need a register, right, to hold the count value. So for that I will create reg, that is I'm not creating a wire data type, I'm creating a reg data type. So 5 down to 0, count underscore reg is my variable, count underscore next. I will tell you why I have created two things. You will understand in a short period of time. So for time being, so I will just open my Word file. 1 second. So we are having a counter right here. So forget about the counter. We are only dealing with the register. So we have a register T Q, and this is this register what we are calling as count underscore reg. Now whatever the value, that updated value is coming to the input of the register, that we are calling it as count underscore next. So who is giving the next value? Combinational logic is giving that next value. How it is giving? By using the current state value. So by using the contents of the register. So since we are realizing a register, and in the register we are storing a value, that's why I have taken for the naming convention count underscore reg. Since this is a sequential logic having a clock signal, this count reg whatever I have declared in Verilog, this will be the pure register. Why? Because this will be updated with respect to a clock. This will be considered as a pure register or the actual register. But count underscore next, this is coming from the combinational logic. So this is just an update. Maybe you can consider it as a wire, but actually it's not a wire data type. Why? Because we are going to deal with procedural statements. So as I mentioned earlier, when you're dealing with the procedural statements, all the left hand side entries should be of reg data type. So this reg is nothing but this is reg data type. But here the count underscore reg, though this is also a reg data type, it is going to ultimately end up as a actual register hardware. So now how we are going to proceed? So first what you have to write, we have to define our sequential logic. So I'm just giving a comments. For this case, I am using behavioral level of abstraction. I'm not using any structural or a data flow kind of thing. Behavioral with data flow. We can say behavioral with data flow. So because the sequential circuit modeling is very easy in terms of behavioral level of abstraction rather than any other kind of thing. So first we will write the description for our counter register, this register. So how do we proceed? So as I mentioned, procedural statements always starts with a keyword always. Procedural statements generally start with a keyword always. Always at what? At the rate. You have to provide the sensitivity list elements. So our register is sensitive to what? It should be sensitive only with respect to clock. So whenever a clock is coming, it should be dependent on clock. So with respect to clock only it should work. Now when you are coming to a clock, you can make it sensitive either to the positive edge of the clock or a negative edge of the clock. That is your choice. So I am choosing positive edge of the clock. So there is a reserved keyword called POS, pos edge. That means positive edge. So positive edge of what? Clock. In our case, the clock is nothing but a clock input. So CLOCK, clock. So always at the positive edge of the clock, begin and end. So within this begin and end, you have to describe the behavior of your counter register. Okay. So first, what you need to define. Reset. So you this counter register, whenever a positive edge of the clock is coming, that is fine. When reset is applied, what it needs to do. When reset is not applied, what it has to do. That also we need to define. So if reset begin and end, else begin and end. And you can notice one thing here. In the sensitivity list, I gave only positive edge of the clock. So assume that this is a positive edge of the clock, but you gave a reset here. Before the arrival of a positive edge. So which will be having high priority, whether a positive edge or a reset? So if you look into this always block statement, this always block is sensitive to only the positive edge of the clock. It is not sensitive to any of the signals. So even reset is coming at this time period, your circuit will not get reset. Why? Because your circuit is only sensitive to the positive edge of the clock. So your reset will not apply outside the positive edge. So in this case, your reset should be at least one clock cycle duration, so that whenever a positive edge comes at this instant only, your circuit will get reset. That means your counter register will get reset. So this is called synchronous reset. This condition is called synchronous reset condition. That means even though you are applying the reset, that reset will become effect only on arrival of a particular clock edge. At that time only the reset will actually work. So those type of circuits are having a reset. So that reset we call it as a synchronous reset. But however, if you want, whenever the reset is coming, irrespective of the clock, you want the circuit to get reset, then what you have to do is, in the sensitivity list, you should also include the reset condition. So the reset is posage of reset. Yeah. So in this case, now you see in the sensitivity list you gave clock as well as reset. So two signals you have provided in the sensitivity list. So when either of the one arrives, the always block will become active. So even when the clock edge is not coming, if you give a reset, it will immediately reset the circuit and it will not wait for the arrival of a clock edge. This type of reset is called asynchronous reset. So it purely depends on what type of a circuit that you want to realize. So there is nothing wrong in designing a synchronous reset or a synchronous reset. So it generally depends on your specifications. So when a reset is coming, and one that too you have to make sure, here I gave if reset. If reset means by default it will take a if reset or if reset double equal to 1 tick b1, both are same. So either you can write if reset or by default or 1 tick b1. That means if reset is logic high, so both the meanings are same. Sometimes this is called active high reset. Some circuits you will find active low reset. So it will reset at logic low and reset. It will not reset at logic high. So if your circuit wants to be reset at logic low, you have to give tilde reset. That means if reset equal to 0, this is also correct, or else you can give reset double equal to 1 tick b0. So anything is correct as per your convention you can follow. So if reset, what it needs to do. So whenever a reset is coming, the internal counter register should be initialized to a 0 count value. That is our initial condition, right? So that only we have to write here. So what I'm writing is, what is our register name? Count underscore reg should be equal to 6-bit decimal 0. You can give 6-bit decimal 0. If you are giving 6-bit binary, means you have to enter 6 times zeros. 1, 2, 3, 4, 5, 6. 6 binary zeros. Instead, you can give 6 tick D0 as well. So both the cases are acceptable. And you can notice one thing I have given here, less than or equal to. So what is a big difference? This is again as per the Verilog Convention. So let me take a new page. So in Verilog we have A equal to B, B equal to C, C equal to D. So this is one type of assignment. A less than or equal to B, B less than or equal to C, C less than or equal to D. This is one kind of assignment. So equal to means blocking, less than or equal to means non-blocking as per Verilog language constraint. So in non-blocking case, this non-blocking, that is less than or equal to, non-blocking will always be used for sequential logic circuits, and the blocking statements equal to A equal to B, B equal to C, C equal to D, these are blocking statements. And these are A less than or equal to B, B less than or equal to C, C less than or equal to D. These are non-blocking statements. So blocking statements are used for modeling, combinational logic, and non-blocking are used for modeling sequential logic. So what is the big difference? So the big difference is that on arrival of a clock edge, maybe positive clock edge or a negative clock edge, as per your choice. If there is a block, if you consider this entire three statements as one block, in case of non-blocking statements, on arrival of a clock edge, all the right hand side will get evaluated and will be assigned to the left hand side at the same time. So immediately A will be updated with B value, B will be updated with C value, C will be updated with D value on arrival of a clock edge. It's not like only one element, even you can put A less than or equal to B plus C plus A. So this is called evaluation. So all the right hand side entries will be evaluated. You can write in one block maybe 100 statements. All statements are non-blocking. Then all 100 statements on the right hand side will get evaluated and will be assigned to the left hand variables at the same time on arrival of a clock edge. That is non-blocking. In case of a blocking statements, as these are combinational logic circuits, irrespective of the clock it will work, but when you are writing in a particular block and you are using it, so the assignment will be in this sequential order. So first you have written A equal to B, so B value will be stored in A. After that, B is equals to C. Old B value is replaced with C value. Next, C is equals to D. D value is updated in C by overwriting the old value in C. So like that, in a sequence order, instruction by instruction, statement by statement will get updated. So this is the difference between blocking and non-blocking. So we'll use non-blocking for modeling sequential circuits. That's why I used less than or equal to. And one of the important major thumb rule in Verilog is don't mix blocking and non-blocking statements within a same block. So here I have written counter edge less than or equal to 0. I cannot write in this block again maybe another statement A equal to B. I can only write A less than or equal to B, because if within a particular block you have to maintain uniformity. You have to use either the blocking or non-blocking. So that is the scenario. If reset is coming, what we are doing, we are resetting the counter register to a 0 count value, so that is 0. And if reset is not coming, what we have to do? Suppose there is no reset, then what we have to do? On arrival of a clock edge, that means on arrival, here we are saying like on arrival of a clock edge, if at all reset is there, you reset the counter register to 0. Suppose if reset is absent and a clock edge has arrived, then what you have to do? What you have to do means, whatever the value in the count underscore next, that is whatever the value coming onto D, that should go to Q. What it's like a D flip-flop, right? So whatever the value coming on D, it should store into the flip-flop, and that value should go out of the Q. So here what is that input? Input to the register is count underscore next. So what we have to write? Count underscore reg is less than or equal to count underscore next. And another thing you can see, for if statement I have written begin and end, for else also I have written begin and end. So if there is only one statement, then no need to write begin and end, you can skip it. But if there are more than one statements, it is mandatory to put begin and end. So for your understanding only, I get to begin and end. So even for one statement also you can keep, it's not a problem. So for your better understanding, I have kept it like this. So now we have modeled our counter register perfectly. So we have defined all the conditions. When positive edge of the clock is coming, if reset is available, then you have to reset the register. Otherwise, you have to update the register with a new value. That new value is provided by the count underscore next. Up till here we have completed. Now we have to define how the count next value is generated for the register. This count next value is generated by the combinational logic which is sitting adjacent to the register. So how do you model that? So for that, again what you are doing is, now we have to define combinational logic. So this is for updating the register. As again we are modeling it by the procedural, since we are using behavioral modeling, we have to use procedural statements. So for procedural statements, always begin with always, begin and end. Always means not just like a keyword always at the rate what you have to define. For a combinational circuit, you can keep simply star. Why? Because the sensitivity list is empty. We don't have, star means it is sensitive to all the signals which are present in the module. If you want to clearly define any sensitivity list, you can define, but the safe side rule is you put a star. So we don't have any sensitivity list with respect to clock. Other than the clock, it has to work for all the time. Whenever there is a change in any signal, it has to work. That's why by default we will use star. Otherwise you can still keep brackets and you can list the things, but a safe side we will put it as star. How we are defining the combinational logic? So combinational logic means how we need to define. So actually, if you consider our black box, if actual counter, I'm not talking about counter register, I'm talking about actual counter module. In terms of a module, we have clock, we have reset, and we have an enable, and we have a count output. And the counter should count whenever the enable is high, and it should not count whenever the enable is low. So that only we have to write. If enable, what it has to do, else in and n. So whenever enable is coming, means whenever enable is active, then what it has to do? It has to increment the value of the counter register and provide the updated value on the count underscore next. So count underscore next is equals to count underscore reg, the register value incremented by one tick binary 1. You can keep one tick binary 1, or else since this is a counter of 6-bit, you can give 6 tick binary 0000001, that is also correct, or else 6 tick decimal 1, that also you can keep it. So as per your choice. So I will use 1 tick B1. So I have incremented the counter only when enable is high. So you can see here, this is a procedural block because we have used always, and this is the left hand term, that is count next, and this is a right hand term. So right hand side term is assigning to the left hand side term. So as per the procedural statement rules, the left hand side term should be a reg type. That is the reason on top here, count next, I kept it as a reg type. So here count next is a reg type, but count reg is also a reg type. But in hardware point of view, count reg is ending up as a register. Why? Because we have given the conditions for the count reg, uh, updating of this reg with respect to a clock that is placed in the always block. So this will ultimately end up as a register, but this count underscore next is not a register. Maybe it can be treated as a wire itself. You can understand it to be as a wire as shown in this diagram, but it is not a wire data type in Verilog, it is a reg data type. So whenever enable is coming, we are incrementing the count value. When enable is not coming, what you have to do? Count underscore next should remain equal to the count underscore reg, because the same value, the counter should hold the same value, right? It should not increment the counter when enable is low. It should retain the last counted value. That means when enable is 0, this count reg value will go to the combinational block, and the same value comes to the D on the count next, and that value again goes into the register. It's like circulating the same value, means refreshing the same value at each and every clock edge. I think we have completed the description of our counter. I think this much is sufficient. So how do we know whether our design module is working fine or not? So we need to test it. This time we will write a test bench to clearly capture the working phenomenon of our module. So to write a test bench, click on the add sources and click on create simulation sources and click on next. And now click on create file. This is the same like creating a design source, but here we are creating a test bench file. So you can give any generic name, but I will give the same module name, my counter 6-bit underscore TB. This is a notation that I follow. My counter 6-bit underscore TB. TB means test bench for my understanding purpose. And click OK. Click finish. It will ask you to define the port list. You need not define any port list. Click OK and click yes. And now a simulation file will be created. You can see under the sources, anyhow you have seen the design sources, one file that we have created right now. Under the simulation sources, we have two files again. One is the design file, that is actual our design file, my counter 6bit.v. In addition to that, we have created a new simulation file, right? My counter 6bit underscore tb test bench file. So you just open that file. As I mentioned you earlier, in order to simulate your design, a copy of your design file should also be present in the simulation folder along with the simulation test or test bench file. That's why you can see two files here, actual design file and the test bench file. So now in the test bench, we have to place our module and we have to test it. So for this purpose, again, I will just I need to explain one phenomena. Let me take a new blank page. So we are having a test bench module. This is my count 6bit underscore tb dot v. This is a test bench. So this test bench has some inputs and outputs. Okay, so this is a test bench file. For the test bench, we don't declare any port list, so the port list will be empty. We again the test bench also, if you look into this, it will start with a keyword called module and it ends with an end module, and the test bench has a unique name, that is my counter 6bit underscore tb. After that, open brace, close brace, parenthesis and semicolon. That's it. Unlike the module, actual module that we have designed, here our module has a port list, right? So for test bench you don't have any port list, it's an empty list. So to this test bench environment, what we have to do is, this is our actual test bench. In this test bench environment, we have to provide some inputs and we have to observe the outputs. But before that, inside the test bench, we have to place our module. That module is my counter 6bit dot v. Now this module we call it as DUT. DUT stands for design under test. So this is a test bench environment. This shaded region is test bench environment. Inside the test bench environment, we are placing our module, that is DUT, to test it. So that placement is called instantiation. 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 So let me instantiate the module. So instantiation of the module means you have to provide the module name and you have to declare the port list. So first thing is instantiation. So instantiation. So first, how do you instantiate? So first you have to provide your module name, and to that module name you have to provide a unique name. That unique name here in test bench we call it as DUT, that means design under test. Now we need not define what is input, what is output. These keywords we have to remove. So input, output, so everything we need to remove. Even the size of the bus width, that is 5 down to 0, that is also not required, that we have to remove. Now what we have to do? For all these ports, what you have to do is you have to place a dot before each port name. This is as per the convention, I will tell you. And then at the end of the port name, you have to keep this parenthesis. For your good visibility, I will just align them. Yeah, this is fine. You can save it. This is called instantiation. So now if you just save it, after saving, you observe these sources. If you observe the sources, after it is getting updated. After update, you can see under the simulation folder, now there is only one main file, that is the top file. You can see the file, beside the file name, there are three dots in triangular in shape, that is called top module. So on top module, you have the test bench file that you can address it by _tb. With that notation, you can understand like this is a test bench file. If you expand it, beneath the test bench file at one step lower hierarchy, inside the test bench, you have an actual DUT. The DUT is nothing but your actual module, my counter 6-bit. That means this is evident that inside the test bench environment, you have placed your module. So that is the significance. So on top, you have a test bench. At the bottom, you have the actual module sitting inside the test bench. Now, what is the key role of the test bench? Now, inside the test bench, you placed your module. This module is having 3 inputs, right? And 1 output. Now, what you have to do is, you have to connect these 3 inputs to the inputs of the test bench and connect this output to the output of the test bench. So, but here in the port list, we don't have of the test bench, we don't have any port list. So port list is empty. Then how, from where you are getting the inputs and outputs of the test bench? So for that, you can declare inside here itself. So inputs, you have to declare, and you have to declare outputs. And here there is one convention. As per the Verilog Convention, only for the test benches, all inputs should be of reg data type and all outputs should be of wire data type. This is as per the Verilog Convention. So from the input point of view, I require 3 inputs, and from output side, I require 1 output. So without any loss of generality, what I do is I reuse the names of the same port list of our actual module in order to avoid confusion. So for that, what I do, reg block semicolon reg. Here it should be end with semicolon. Why? Because it is not a port list. Inside the port list, you will put comma, but outside the port list, each and every statement should end with a semicolon, so that you keep into mind. So clock, reset, and enable. And the output should be a wire, right? So wire, and the width of this wire is 5 down to 0, that is 6-bit. The wire name is count. Okay. So this is done. So why I use the same name means it will be easy for me to connect the test bench input to DUT input and test bench output to DUT output. So for the ease of convenience, I have used. So now what you have to do, you have to make connections. So this is a clock of test bench connected to the clock of the module. Next, reset of the test bench should be connected to the reset of the module. Enable of the test bench should be connected to the enable of the module, and the count of the test bench should be connected to the count of the module. And please note that the right hand side clock, reset, enable, count, what I have highlighted belongs to test bench, and left hand side clock, reset, enable, count that I have highlighted belongs to the module. and this clock is different from this clock, this reset is different from this reset. In order to avoid confusion, I have reused the same names, but however they are different. You are free to use different names for test bench inputs, test bench outputs, and module inputs and module outputs, but you should be very careful in mapping the ports exactly, properly. So inputs is defined, outputs is defined, and instantiation has been done. Now what we have to do is we have to define the initial conditions. Initial conditions of our test bench variables. See, we are standing here and we are giving inputs, right, to the test bench, and here we are observing the outputs. So from here we are driving the stimuli. That means we are giving the inputs to the test bench. That inputs are passing to the module, and module is generating output. That output you are capturing it here and we are observing it. So first of all, the input should be initialized to their initial condition. After that only you have to give your inputs. So in the initial condition, there is a procedural statement called initial, 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 begin and end. Initial, begin and end, this will only run for only one time. See, initial block, this is only used in the test bench. This is also a type of a procedural block, but this will not be used in a design file. In design file, we will only use the always procedural statement block, not the initial procedural statement block. The initial statement procedural block will be mostly used in the test bench. As the word says always, throughout the infinity period of time, that always block will be active, but initial block, whereas as a keyword suggests initial, it will only run for an initial time period and it will stop after executing all the statements. So in the initial condition, what you have to do, what are your inputs for your test bench? Clock, reset, enable. So these things you need to define the initial values. So initially my clock should be 0, reset should be 0, and should be 0. You can ask me one question, how I wrote 0 0 0. It should be one tick binary 0, one tick binary 0, like that. We have to define, right? Then why you have defined a decimal 0? Why? Because in hardware decimal 0 has no equivalent. It can be, if you give 0 means how many bits of 0, that is not defined. It becomes ambiguity. But for the test bench, you have a little bit freedom. Since your test bench is only meant for testing the module, not for realizing a hardware. So in this case, this will work. But in the design files, don't give like 0, 1, 2, 3 like that. So it has no significance and it will lead to an error. The tool will not understand what's in your mind. How many bits of zeros or how many bits of ones are you are requesting for. With that only the hardware needs to be realized, right? So the tool will not have an idea of what's in your mind. So whenever you're designing anything, you have to clearly define how many bits. See, in the design folder, in the design file, I have used one expression, count range is less than or equal to 6 tick D0, 6 bits which of decimal 0. So decimal 0 equivalent representation in 6 bits, equivalent representation in binary having 6 bits. That value will be stored in this count register. So here you have to define everything properly, but in the test bench you have a little bit freedom. You need not define. Why? Because you are not actually realizing any hardware. Only thing is you are actually testing your hardware. So initial conditions has been set. And one more thing, since this is a sequential logic, mainly dependent on the clock signal. So in the test bench environment, you have to generate a clock signal to drive your module. You need to generate a clock signal and you need to drive the clock signal to the module. Then only your module will actually work with reference to the clock signal. Otherwise, it will not work. So in the test bench, it is mandatory for you to generate a clock signal for a continuous period of time. Why? Because you may run the test bench for an infinity number of time, where that infinity means it has a finite value as per the user specification. I may run for 1000 nanoseconds, some other user may run for 1000 picoseconds, another user may run for 1 second. So the time is variable. So when the time becomes variable, the circuit, if he wants to test it for all the period of time, he should be able to give the necessary clock signal to the circuit. So for that purpose, you have to generate an infinity time period. You have to generate the clock signal for infinite period of time. That is, as long as the simulation is valid, you have to continuously generate the clock signal. So for that purpose, what you have to do, you have to use an always statement. So as the keyword always suggests, it will generate as long as the simulation runs, a proper clock signal will be provided. So again, how this clock signal should be provided? Always, each clock should have a time period, right? So I want to create a 10 nanoseconds clock. So 10 nanoseconds clock means, so this is one clock cycle, right? So positive edge to positive edge, this is 10 nanoseconds. If you take 50% duty cycle, each on period and off period has 5 nanoseconds. So for 5 nanoseconds, the value of the clock should toggle from 1 to 0 and 0 to 1. So that is what how I'm defining is always with a delay of 5 nanoseconds, clock is equals to negation of clock. Just a minute, I need to charge my laptop. Okay. So what is this 5? This 5 is for nanoseconds. You can ask me here, I gave only 5 and how I am sure like it is in the order of nanoseconds. If you scroll up little bit, there is a primitive called time scale 1 nanosecond slash 1 picosecond. So this is a time scale is operating at 1 nanosecond with a resolution of 1 picosecond. So each time unit is of 1 nanosecond duration. So that's why here I gave a delay of 5 means it is 5 nanoseconds. So I have got a clock of 10 nanoseconds time period. That means 100 megahertz. Just a minute. Just a minute. I have an. Yes. So the clock signal has been generated. Now finally, we have reached to the end stage of our actual test bench. So what is the purpose of writing the test bench? We want to just verify the functionality of our module. So we have our counter module, we have an enable signal and we have a count signal, and here we gave a reset signal. Clock is coming continuously, so this we have generated, and we have a reset enable. So we want to observe the behavior of our module. So when reset is coming, how the circuit is behaving, when reset is removed, and when enable is given, how the circuit is counting, and when enable is stopped in between, and how it is returning the count value, and again when the enable is resumed, how it is counting. So these all conditions we need to observe in the form of a timing diagram, right? So in order to study all these things, we need to provide appropriate stimuli to via our test bench so that these stimuli will go to the design under test. That is our module, and accordingly we can observe the functionality. So the final step in our test bench is to provide stimuli. So that we call it as test stimuli. And this stimuli you can provide only for this stimuli should work for only one iteration. This stimuli should not work for forever. Means it should not work in a continuous loop. Again, if you write always begin and end, this stimuli will be given over infinite period of time continuously, but we don't want that scenario. We want to just model all these cases and check the functionality. For that, again we will use an initial block. Initial, begin and end. So within this initial block, we have to define our test stimuli to verify the functionality of our module. And you can see here, this initial block first will be get executed. After that, only this initial block will get executed. No, sorry. Actually, this initial block is a procedural block. This initial block is again a procedural block. This is a always block. So all these three blocks will work in parallel. So that you need to keep in mind. So in this initial block, we set all the initial values to 0, and this will run only for one time. So first clock will be set to 0, reset will be set to 0, enable will be set to 0. After that, this initial block time period is over. It will not work again. So at time t is equals to 0, this block, always block, and this initial block will work in parallel. And within the time t equal to 0, all these internal signals will be set to 0. After that, this initial block has no significance. It will go out. This always block anyhow will work in parallel continuously for entire period of the simulation, and this initial block will work until all the statements are executed at least once. Once all the statements are executed, this also becomes invalidated. So this is the case. Now we will take at least 5 minutes of break. After the break, we will see how to give the test stimuli, and then we will check the simulation. After that, once simulation is validated, then we will proceed with the further steps. You can take some 5 minutes break. In the meantime, if any student has any queries, earlier Mahesh sir has said that someone is facing an issue. If you want to discuss, you can share your screen from your end to discuss. Otherwise, we will see at the later stage. That's it from my side. Mahesh sir, please take control.
Yes, sir. We will join after 5 minutes.
Okay, sir. I will also join in after 5 minutes. Yeah, welcome back. We will continue. Um, but before that, please let me know whether my screen is visible or not.
Yes, sir, it's visible.
Okay. Yeah. So we have stopped at the test stimuli. Now we need to give the test stimuli, right? So how do we model our test cases in order to verify the behavior of our circuit? So we have our counter register, right? So in the counter register, so we are giving a continuous clock signal, and we are giving a reset signal, and we need to give enable input, and we have to observe the count output. So the first case is how do we write our test cases? So first scenario, what we need to do is first we have to reset the circuit. So for that, what I am doing is I am applying reset after a delay of 10 nanoseconds. Reset equal to 1 take B1, and this reset should be valid for some time period. So after that, I want to release the reset. You need to release the reset, so the reset condition will be verified. So after a time, disabling it. Next, we need to monitor the condition of enable. So first, what we do is we make the enable to be high. So for that, after a delay of 10 nanoseconds, enable. So as soon as the enable is high, at each and every clock edge, our counter will run and it will increment the count value. So at each and every clock edge, as per our design, we are going to expect a count value. So that is keep on changing with respect to a clock edge. So when enable is what we do is before the count value reaches the maximum count value, we make the enable 0 for some time period, so that this is enable, we will make it at this point, and we will see whether actually it is retaining the last count value or not. After some time, again we will make the enable high, and we have to observe whether from that point again it has resumed counting the values or not. So for that, in order to observe this scenario, what I'm doing is after a long time gap, maybe after 200 nanoseconds, I am making enable to be 1 take B0. Okay, I'm turning off the enable to check this condition, this time period, whether it is retaining the means whether it is holding the count value or not. After that, what I'm doing is I will make the enable to be high. So again, this enable I will make it for 100 nanoseconds. And before the count value reaches to a maximum count value, I want to apply a high reset signal, so that I want to see whether the reset has the highest priority or not. So even in the middle of the counting stage, if I give a reset, whether the count value is abruptly turned off and it is reinitialized to 0 or not, that I want to check. That is one condition. So for that, what I'm doing is, again, after a time gap of 100 nanoseconds, I am making reset equal to 1 let be 1. And you notice that here I have not disabled the enable signal. I have not turned off the enable signal. So the soon after releasing the reset signal, I just wanted to make sure whether it is immediately whether the counter is immediately restarting the counting operation or not. So that is a release option. And finally, somewhere again in the down the line, after some time period, I want to turn off the enable. So this is one particular scenario, a random scenario, maybe you can say, I have considered in this fashion. You can also consider your own kind of a scenario in order to test, because when testing you should test your circuit by covering as many corner cases as possible with some randomization, because we need to observe the how your circuit is going to behave when for all the set of random inputs. And so for better understanding, I will just align it properly. Earlier, if you observe, for the combinational circuit, we have not designed any test bench. We have directly, what we have done is we have directly launched the test bench. We got a blank test bench. In that, what we have did for each and every signal, we forced some values and we have observed we have forced the value, run this test bench for some time, observed the response, again changed the forcing value, again observe. That we have done manually. If one or two signals you can do manually, here in this example we are dealing with two signals, reset, enable, and every time we are changing the combinations of the reset and enable signal. Say for example, again you have 1000 set of signals, so each and every time you cannot force the each and every signal manually. It is a very big tedious task. So that's why we will use a test bench file similar to like this, wherein we feed all the test cases covering all the corner cases, and then we will run the simulation, this test bench, so that while in this simulation environment, by using all these test stimuli, it will perform the simulation and will give you the output. So once these test stimuli are given, you just save it. After saving it, what you have to do is you have to check here in the design sources. Our module, what is our interested module? Our module is my counter 6-bit. If there are n number of modules, whatever the module that you want to test, that should be the top module. Here unfortunately we have only one module, that is by default it is the top module. In case if there are more than one module, what you have to do is whichever the module you are going to test it, that module you have to select. You have to click on right click, and here you can see set as top. However, it is by default set as top, that's why it is disabled. So this option will be available, so you have to set it as top module. Similarly, in the simulation folder, again you have to select an appropriate test bench file under which the same module has been instantiated. That test bench file, again you have to set it as top module. So once these two are set, then only you have to launch the simulation. Otherwise there will be a mismatch will happen. So you have to make sure that always in this test bench environment, you select a proper test bench environment, and within the proper test bench environment you have instantiated the appropriate module. That you have to make ensure. Once this is fine, then you click on run simulation. In that you select run behavioral simulation. So once you click on run simulation, you got a timing waveforms like this. You can just maximize it. You can click on zoom fit. So here you can see clock is running continuously. reset conditions, whatever we have given in the test bench, appropriately conditions are coming. Enable is also getting toggled from 0 to 1, 1 to 0, and 0 to 1, so on and so forth. But we are not getting any output. Why we are not getting any output? So here it is showing a high impedance Z. High impedance Z indicates that there is a hanging output. That means the output of your module is not connected either to the test bench, or within the module the output is not properly driven by any of the net. The net may be either a wire or a resistor. That's why we will be getting a high impedance. So where is the problem? The problem is either in the test bench or in the module that we need to debug. In the test bench, we have a counter that connected to the count of our module. So there is no problem in the test bench, and I think problem is in the Verilog module itself. So here you can see in the Verilog module we have a count output, but what is driving this count? Actually, in as per our diagram, the count register value should drive the count output. That means count reg should drive the count. So we have defined the sequential logic and we have defined the combinational logic. This is fine, but we forgot to drive the count register to the count output. So that how we will do is this is the output logic. So here you can see the sequential logic. We used always statement, that is a procedural block. That means this is behavioral modeling. Again, for a combinational logic, we used a always block, that is a procedural statement. That means this is behavioral modeling. Now in this always block, we are updating the register, right? Count register with respect to a clock. This register contains the actual count value. This value should pass to the output. So what I am doing is I am connecting the output to the register. So using an assign statement. Assign is a non-procedural statement. So non-procedural statement means it is a data flow modeling. So in this example, we have two different modelings, two different level of abstractions that we have combinedly used. That is behavioral modeling and data modeling, data flow modeling. So we used assign count. So counter reg is connected to count output. I think now you can relaunch this simulation. So if you could relaunch this simulation, now you should get the actual output. Okay, the output is coming. So what we do is we keep a test bench as our reference. Okay. First, whenever you got a test bench, click on the 0 to timestamp and just zoom it over there. And you observe clock reset enable is 1 bit. It is in binary format, so not an issue. Next, we have counter.
Sir, excuse me.
Yes, sir.
Yes, sir. A error has occurred. Can you please resolve for this?
Just a minute, sir. After completing this, just give me 5 minutes.
Fine.
So this count actually it is in the hexadecimal format. For better understanding, you can change the radix to unsigned decimal. Okay, now this is fine. Now we will see how our test, you can save it if you want. And if you see the test bench, so first we gave reset. First you will see initial conditions, we give clock reset enable as 0. So if you zoom here, so at the 0 to timestamp, clock is 0, reset is 0, enable is 0. And after 10 nanoseconds, reset is 1. So Here at the 10 nanoseconds gap, reset is 1, and reset is removed after a time period of 10 nanoseconds. So here the reset is removed. So once you clicked on the reset, here before the reset is coming, the count register value is X, undefined. That's why the output line count is also undefined. The moment you give a reset signal, what is happening is the count register is getting reset. So what type of a reset it is? In our module, if you see, we have given, I have given a synchronous reset. Means this will get reset only at the positive edge of the clock. That is the reason why, if you see here, even after applying the reset at a time period stamp of 10 nanoseconds, the count output is still undefined, that is X, and at the next positive clock edge, the output is becoming 0. That means the register has been reset at the timestamp of 15 nanoseconds, but not at the timestamp of 10 nanoseconds after the reset has become active high. So this reset is active high for at least one clock cycle period. So that is the reason on arrival of a positive clock edge, the counter has been reset to 0, and the same reset value 0 is appearing on the count output. So the output is 0. And in this case, the enable is still at 0. That's why it is not counting anything even at the positive, even on arrival of a positive clock edge. So even if you check on the next clock edge also, the enable is 0 and the count value is also 0. So when we have made the enable as 1 after a time gap of 10 nanoseconds, when the reset is removed, after removing the reset and after a time gap of 10 nanoseconds, enable is made high. So enable is becoming high at the negative edge of the clock cycle. So soon after the enable is made high, the combinational next state logic, that is count underscore next, will be immediately updated. But this count underscore next, in order to observe that, what you have to do is, in this scope, you have to select DUT. In the test bench, you have to select DUT. Inside the DUT, you have count underscore next, that you need to add it to the waveform in order to see internal components. By default, you can see only the top level inputs and outputs. If you want to see internal signals of a module, then you have to add it to the waveform. So once you have added, again you run the relaunch so that you will get this signal as well. Now fit it to zone fit. Making the enable, the combinational logic value has already computed the value 1, but this 1 will go into the register on arrival of a positive clock edge. So here when the positive clock edge is coming, this combinational value, the logic value 1, that is going inside the register, and the same value from the register, it is driving the output count. So now the count value became 1. Soon after that, again the enable is still logic high. So the combinational logic got immediately updated to 2 irrespective of the clock, and this value is updated into the register on arrival of a next positive clock edge. So in the next positive clock edge, the 2 is sampled into the register, and that value is driven through the output, and through the count output we are getting the value 2. So on and so forth, the counting is happening, and it is happening for how much time period? Until the enable is made 0. So when the enable is made 0, after 200 nanoseconds, we made the enable to be 0. So if you just scroll like this, so you can see here the enable became 0. Where? Here. At the negative edge of the clock, the enable becomes 0. At that time, the max count value is 20. And in the subsequent clock cycles, on arrival of a positive clock edge, you can see the counter is not incrementing, but however, it is retaining the same value. So the same value is retained. So whatever the count next value, it is going into the count value, and whatever the count value is there, that is coming into the count next. So it's like a circular loop. So combinational and sequential logic are updating in one after the other. So the same count value is retained. Again, this is retaining for how much time? Until enable is made 1. So when again enable is made 1, so when it is made 1, at the negative edge of the clock cycle here. So soon after enable is made 1, combinational logic has updated its value to next value 21. 20 plus 1 is 21, and on arrival of a next positive clock edge, the new value is sampled into the register, and the new value which is in the register is driven to the output, that is count. And this is continuing count until what has happened, the next until since it has not reached to the maximum count value, in between what we are doing is we are resetting the counter. So at the time of counting, see, it has counted 26, 27, 28, 29, 30, and it is still in that process. After counting the value 30, what we done is we have made the reset high. So soon after making the reset, immediately in the next clock cycle, you see after 30, instead of coming 31, we got a value 0. So that means we are counter has abruptly resetted. That means the reset was given high priority and the counter has stopped. And this reset is active for some time period. You can see. So over this entire period, the counter is not counting and the count register value is completely 0. And soon after the reset has been removed, here we see the reset is removed, but enable is not removed. Enable is still high. So soon after reset is removed, since enable is already high, the counter again started to count the sequence, and it is counting until the enable is made 0. When it is made 0, after some time period of 125 nanoseconds, we made enable to be 0. So when enable is 0, the count register has stopped and it has retained the last updated count value. That last updated count value in this example scenario is 12. So now if you run the simulation for n number of time period, since you are not giving any stimuli, only the last updated values will be reflecting for the entire time period, that is time period of infinity. So all our test cases we have verified in our test bench, and the module is working as per the desired functionality. So the what we can conclude from here is that the HDL description, whatever we have written, it is meeting the desired functionality. But we don't know whether that this description is a valid description or not, whether we can get a valid circuit out of this or not. How we will know? We will know once it is perfectly synthesized and implemented. So in this way, generally we will write a test benches to verify our digital circuits. So I will stop over here. And Mahesh sir, you said you have some query with respect to some. You can just tell. Yeah, you can share, sir. I have stopped sharing my screen. Yes, sir. What is the doubt, sir?
There is some compilation error.
Okay, simulation is failed due to error. Sir, wait. You can see on the screen whether the screen is visible to everyone.
Yes, sir. It's visible to everyone.
Okay. So everyone, please pay attention to the screen. When you are launching a test bench and you are trying to run a simulation through the test bench, and test bench is unable to launch the simulation and it has resulted in error. So what it will give you is this dialog box will come, and here you can notice there is it is telling that it has failed, and it is showing you one file name xvlog.log. So there are two files will be there depending on the errors, either xvlog.log or elaborate.log. Two different files will be there whenever you encounter any simulation errors. So at that time you just notice what message is being reflected on the screen, what Vivado is asking you to where it is pointing you. It is pointing to xvlog.log file. So you please go to that path and open that log file. Mahesh sir, you please go to that CFDP lab 2 so on and try to open that xvlog.log file. You have to open from the Windows Explorer, sir, not from the Vivado. So please read that error message, sir. First error, cout underscore reg is not declared, and it is in the line number 50 of mycounter.v. So you please open mycounter.v file and go to line number 50. You have written like cout. I think it is count underscore reg. Now you save it. That's it. That is the only error. Now you try to launch the simulation. Now even then it is failing. Okay, now you again open the xvlog, sir. Close and open, sir. The clock should be reg type, sir. Go up. Okay, clock reset and okay, now fine. I think this should work. Okay, sir.
Yes, thank you, sir.
Okay.
Sir, how to check the output?
Just click on zoom fit. Yeah. Because the simulation will stop at 1000 nanoseconds, so you have to click on zoom fit. Now you just place the cursor anywhere and just click on control and scroll button on the mouse, and you can just check it.
Thank you, sir. Thank you.
Okay, sir. Still anyone have any doubts? We can just take, I think we have just 3 minutes left for this session.
Sir, no doubts from the student side. I think they should have some. They will watch the video again, so let them try on this.
Okay, sir. Now my suggestion from my side is I have shown you a simple counter-based design. The design approach is similar for designing any sequential circuits. You better try with some down counter or up and down combined into one module. You use any control signal. When control is high, it should count from up. When control is low, it should count from down. So like that up and down counter you can design, or else this counter basically starts with a 0 and it's counting to all the states. You can also design a counter which loads where you can load a value and ask the counter to start counting from that sequence. So different type of designs you can just make it and just practice it. Also design a few flip-flops, shift registers, and so on and so forth. My main aim of video is to show just how we will be carrying out combinational and sequential logic designs, and these two we will combinedly use in designing the FSM. So FSM is a very important topic. So after that, once the FSM is familiarized, we can start developing. We can take very big and interesting research problems, and we can start coding and designing our circuits over large or intermediate scale level. Mahesh sir, you can give some assignments to them. Ask them to just design a few sequential circuits by today, and they can show it to you by tomorrow.
Sure, sir.
Am I allowed to continue for some time, or else can I stop it?
Sir, we will continue tomorrow, sir.
We'll continue
because the students has to practice once by themselves, so that to make everything clear.
Yes. Okay, sir.
Okay, sir.
Then tomorrow.
So thanks for.
Yeah, just 2 minutes, sir. Tomorrow we will see. We will try to implement the same code, and but when you implement this code on FPGA, and if you want to observe the output on LEDs, you cannot observe with your naked eye. Why? Because clock is operating at an order of megahertz, and in each and every clock cycle, the count value is continuously changing. If you directly connect this to an LED, LEDs will do blink, but with a naked eye, we cannot perceive that. We don't see any blinking effect. In order to see this, we have to delay the counting mechanism. So for that, there is one kind of a mechanism where instead of counting at each and every clock cycle, we need to count at some after some n number of clock cycles, where that n clock cycles is nothing but a delay equivalent to maybe 1 second or a half second duration. Then only human eye can perceive it and easily visualize the blinking of LEDs. That is one way. In another way, when here input is changed, output is changing at a very rapid rate at an order of a clock cycle. Another way is to visualize this output in real time is by using an intellectual property IP core, which is available in Vivado. So tomorrow we will see how to configure the IP core and attach to our design in order to visualize the output in real time, which is changing at a clock frequency rate. So tomorrow will be an interesting topic, and please don't miss it. Yeah, that's it from my end.
Thank you, sir. Thank you very much for your time and for the wonderful session.
Okay, thank you, sir. Have a good day.
Bye, sir.